Yeah. In this lecture, we will discuss about applications of operation amplifier. In the previous class, I had shown you how to make a voltage regulator using transistor. If we use transistor for voltage regulation, we will have problem due to temperature drift, whereas that problem will not be there if we use operation amplifier. Now, first we see how to make a voltage regulator using operation amplifier, then I will explain some more characteristics of the operation amplifier. Now, for example, we have an input that is coming from a 230 volt AC main, that is I have a AC 230 volt that I feed to a transformer primary, and then I have the transformer secondary here. So, this voltage I rectify then I will get a rectified DC voltage here. So, here what we have done is we have taken the 230 volt AC and then using a step down transformer we have reduced the voltage, and then reduced voltage is rectified, and then we will get a rectified DC voltage. We will see how much voltage we have to select and so on little later. So, you got a rectified DC voltage. This rectified the voltage the whatever voltage that we are getting between whatever voltage we are getting between this point and this point, that actually depends upon what is the mains voltage as well, because if this increases, this voltage also will increase, if this decreases, this also will decrease. But then we want this voltage across this to be constant irrespective of change in the input voltage. That is what we are going to do it here. So, what I do is I will take transistor, then I also, since we want high current, I put a Darlington pair here and then connect the transistor to this, and then this I connect to ground. Then what I do is this I connect operation amplifier to this, I just connect one series resistance and connect to this. Then the output of the transistor I put a voltage divider, connect this to the minus, and then plus input I connect on Zener diode. Then for biasing the Zener diode I put on resistance and connect it here, and here we will get output voltage V0. In fact, we also have to put on capacitor here to the output to ground. Now, this is the voltage regulator circuit using operation amplifier. Now, just let us see how this works and what is the advantage of the operation amplifier we got over and above that what we got from the transistor. Now, first step is you see that we got a DC voltage here, and that DC voltage this DC voltage through this resistance we are applying to this Zener diode. So, if you see only this part now, this is only used to bias the Zener diode. So, assume that my Zener voltage is 5 volt here, and say the Zener can be a very good Zener, like for example, we have Zener like LM336 is there, which is a band gap Zener, and this is very stable against temperature. For example, with temperature the voltage changes only 30 parts per million. So, we call it about 30 ppm Zener, because for Zener it is a very important spec, how much voltage will change with temperature. Now, I have to bias this, for that I had used this resistance R1, that is through this R1 only current is flowing to the Zener. This Zener needs about 1 milliampere current. Unless 1 milliampere current goes through that, you will not get 5 volt correctly here. So, I had to get 5 volts. So, I had selected it such that 1 milliampere current goes all the time. Now, assume that I have some voltage at this point. Now, how much voltage I need, that depends upon what is the output voltage that I require. Now, for example, if I take this is 20 volt, that means this is 5. That means the voltage across this, if I take this, if this is, if I take it as 20 and if this is taken as 5, then you have 15 volt across this. Then if I need to keep 1 milliampere current flowing through this, then I have to take 15 volt divided by 1 milliampere, that will give me 50k resistance, because I have to maintain 1 milliampere current. Anyway, the current flowing through the input of the op amp is small, so I have to keep 15k. So depending upon this voltage and the current requirement, I have to select this resistance. In this example, by taking this this voltage as 20 volt, this comes at 15k. So now this voltage is 5 volt. Now you have output voltage here, and assume that I have put the resistance, say here 10k, and assume that I have put 10k. We will talk about these values little later more in detail. Assume that now this is also this and this are 10k. Then it means that whatever voltage that we are getting here V0, this will be V0 by 2, because this is merely acting as a voltage divider, and there is no current flowing through this. So if this is say 10 volt, then this will be 5 volt. That means whatever voltage is here, half of that it is coming here. Now you see what is happening in the op amp, that this point is kept at 5 volt fixed, and this point depends upon the output voltage. Suppose if this voltage is higher than 5, because this is this point is at 5. So if this goes higher than 5, then the operation amplifier output will be the difference between these two multiplied by the open loop gain. The open loop gain of the op amp is, that is without any feedback, what is the gain that this op amp is providing. Even for the simple general purpose operation amplifier, the open loop gain will be around 20,000. So we say the open loop gain is around 20,000. That means if this is 5 volt and if this comes to 4.999, it's just 1 millivolt difference. Assume that this is at 4.999 and this is 5, then you can expect this difference of 1 millivolt multiplied by this 20,000, that is what is supposed to appear at this point. Now what is happening is, the difference 1 millivolt multiplied by 20,000 will give you 20 volt at the output. Now this operation amplifier also needs power supply. So what we do is, normally we will apply power to this op amp, and that invariably the same as what actually given here. So we connect the op amp here. So this 1 millivolt difference turn as 20 volt at this point, and assuming that this current is very small, base current is very small, then the 20 volt here, 20 volt at this point will appear as 20 volt here, and then this 20 volt actually will become 19.4 volt at this point, because you need base emitter voltage difference of 0.6. The 19.4 will appear as 18.8 again, because you need only 0.6 volt difference between base and emitter. So 19.4 volt here will come as 18.8 here. So then 18.8 will be appearing at this point. If the 18.8 appears, then this will go 9.4 volt. The 9.4 volt is much higher than 5 volt. So now this is higher, this is lower. So the difference is 9.4 minus 5, that is this point is higher by 4.4 volt. That means output supposed to go minus side, that is 4.4 volt into 20,000, that much minus voltage come. Anyway we have no minus supply, so the output of the op amp drops to 0, because it can't go to minus side. So the lowest what it can go is 0, so it goes to the 0 volts. Once it goes to 0, this also goes to 0, then output will also tend to 0. If the output goes to 0, then this also will become 0. Then once this is 0 and if this is sitting at 5, if this is 0 and if this is sitting at 5, then again output will go, the difference is extremely high, the 5 volt into 20,000 have to go to some 10,000 volt and so on, but that much is not possible. So whatever supply voltage is there, 20 volt, the 20 also will appear here, then again this will 20 and 19.4, 18.8 will come, again this voltage will increase. Now like that, if you see, this chap has to go on increase and decrease that to happen. But in reality what happens is that once if this is set at 5, this chap start rising, and then we know if this is voltage across this has to be 5, then voltage across this also will be 5, and this has to come to 10 volt. If this has to come to 10 volt, if this has to come to for example, if this point has to come to 10 volt, I know that this voltage has to come to 10.6, this has to come to 11.2, and if I assume the drop across this is negligible, then this is 11.2. We know that to get 11.2 I need some difference. So what is the difference that we need to get 11.2? Because if I need output 11.2, then 11.2 divided by open loop gain, that is 20,000, is the V difference required. That is difference between these 2 points should be this much. So if I calculate this, that will be roughly 11 volt divided by 20 into 10 power minus 3 millivolt. That roughly comes 0.5 millivolt, nearly 0.5 millivolt difference. That means if this is sitting at 5, then obviously this has to sit at 4.9995 volt. That is only 0.5 volt difference, that this is less, this is more, and then you got 0.5 millivolt multiplied by 20,000 will gives you around 11.2 volt, and 11.2 comes 10.6, and this comes to 10, and that roughly gives you 4.995. So eventually what is happening is, if I keep this at 5, this comes very close to 5. All practical purpose I can take this also coming to 5, and that means voltage across this is 5 and voltage across this also 5, and output goes to 10. Now by some reason, if this voltage trying to go more than 10, if this voltage goes to more than 10, then this will go more than 5, then if trying to go more than 5, this will start decreasing, then output will decrease. If this decreases, then this will also try to go lower than 5. In case if this try to go lower than 5, then this voltage will increase and output also will increase, and then to make sure that this point is always kept at 5 and this point is always kept at 10 and this point always kept at 5. This is how the operation amplifier regulates. So if you carefully watch that, what the operation amplifier doing is, whatever voltage that is given to plus input, the same voltage forced to come to the minus input because of this feedback, because of the closed loop feedback that is taking place here, and also because there is a high gain in the operation amplifier. And so what is happening is that if I keep here 5, then automatically this is this have to stay at 5. Actually it is not exactly 5, it is little less than 5. The difference whatever that you are getting, that multiplied open loop gain is what is put here, and that is what it is coming here. So very small difference is maintained to generate this 10 volt, because the open loop gain is very high. Now this is very important, because all that I have to worry is that I keep this 5, then I know I will get 5 here, and if I want for example 15 volt, what I do is I will remove this 10k, I will put here 20k for example. In that case, then this 10 volt will disappear now. Assume that this is, you have some higher voltage here, then what happens is, I know that across 10k it is 5 volt. Then since the same current is flowing through this, across 20k it must be 10 volt, because across 10k if I get 5 volt, across 20k I have to get 10 volt, then total voltage will be 10 plus 5, then I will get 15 volt here. So in this case I will just get 15 volt. So that means all that I need is, if I want to change the output voltage, I will change either this or either this, or I change the Zener voltage. So, the essentially we can say that the output voltage, if I see the output voltage V0, output voltage can be written as V0 is actually the V reference what we had divided by, assume that this is your R3 and this is R4, then V reference by R3 into R3 plus R4 is the relation between V reference R3 and R4, because VR by R3 gives you the current through this, then the same current is flowing through this. So, total voltage will be total resistance into current, that is why we have put this is current into total resistance R3 plus R4. So, that gives you the relation for the output voltage. Of course, you can adjust this or adjust this or adjust this to get any voltage you like, provided input voltage is more than the output. For example, if you want 15 volt, then I need to have minimum of 15 plus 3 volt drop is required for the transistor to work. So, I have to get at least 18 volt here. So, if I need 20 volt, I need to get 23 volt here. So, as long as I have sufficient voltage at the input, I can get whatever voltage that I need by varying either this or this or this. Now, this is how the regulator is working. Now, in fact, the working principle of the transistor regulator also same that we had seen in the previous class, but then the difference here is that if temperature of this operational amplifier changes, you will find there is very little change in the output, because we had shown in the previous class that in the operational amplifier the temperature drift introduced by the transistors, that basically the VBE change due to temperature is compensated and they have very little effect. So, if this is 5 and this always come to 5, and with the temperature whatever the change that it demands is very small, that are all in microvolts. So, whereas in transistor the base emitter voltage changes 2.2 millivolt every 1 degree C, whereas here it changes only few microvolt. That is the difference in between the two base emitter voltage change, that alone will be coming here. So, that is one of the great advantage using the op amp, and then now we have the op amp with very high gain, that also gives us makes us assume that if I am sitting, this is at 5 and this is also coming at 5, that we can assume because the gain of the open loop gain of the operational amplifier is very high. So, this gives us good insight into how the op amp operational amplifier is useful, and then how it is very easy compared to the transistor in using the electronic circuits. Now, this is how the basic regulator is working. Now, let us see how to make a practical voltage regulator, that is how to decide on this transformer. Then we had also decided on this we had decided on this capacitor value and how to select the diodes, then how to select these transistors, and then the transistor also dissipate heat and we need to put a heat sink for this, and then why you need this capacitor here. All these things have to be decided, then only you will get a practically working circuit, because in real life if you make a circuit that must be practically usable, and only then it has any value. A simple textbook circuit really has no value and it has only academic interest. So, we have to make a circuit which is really useful, and someone wires that must work without giving any problem. So, from that angle now we see how to design a circuit. Assume I need 15 volt output to use in some circuit, and then at the maximum I also have to draw some current here. Assume that this is my load resistance, and my load resistance my load resistance never going to be less than 15 ohm. In the sense I am not going to draw more than 1 ampere current, here. So, that means I am fixing first what is my output requirement. That is, my output requirement is 15 volt, 15 volt, 15 volt at and 1 ampere current. I am not, the 1 ampere current means I am not going to draw more than 1 ampere, I may draw less than that. So, this is my output requirement. So, I had fixed my output requirement. Then if I need 15 volt here, I should fix what is the required voltage at the input here. If I need 15 volt, then I need to have at least 18 volt at this point, because the transistor needs minimum 3 volt to be effectively working, because we have to reverse bias the base collector junction that needs actually minimum 3 volt. So, we need 18 volt at this point. And also I had to see that the 15 volt is here, and when the even when the mains voltage, for example, the mains voltage is 170, then also I want if this 170 also I want the output to be 15, even when 270 the output to be 15. That means if the output voltage has to be 15, then I know that input has to be 18. That means I need to get 18 volt here when the input here is 170, because at 170 I should get 18, then only at 170 I will be able to get 15. Of course, when the input voltage goes to 270, this will go much higher than 18, and that does not matter, that anyway that 15 volt will be here, and the extra voltage will be dropped on the transistor. That work is done by the operation amplifier automatically. So, next that what we have to fix is what is the input voltage range. So, input voltage range is input voltage range is 170 to 270 volt. That is from 170 to 270 input I should get constant 15 volt. If the voltage goes below 170 volt, output is not going to be 15 volt. That is what we are accepting it by telling that input voltage range is 170 volt to 270 volt. So, having fixed the input voltage and then the output voltage and current, now we can decide what is the rating required for the transformer. Now, if we take this, now the input voltage, the voltage that we need at this point is minimum 18 volt. So, if 18 volt is what is required minimum, and that is at 170 volt, then we know that when if I have a AC voltage here, if I am rectifying and then connecting to a capacitor, the capacitor charges close to the peak value, because if I look at the voltage at this point that you have, I will show you in the next diagram. See, the input voltage is if I draw the rectifier schematic, then the second primary you have, then the secondary. Now, the diodes we are putting it here. If I see the waveform, that say this is A and this is B and this is my ground point C and this is D, then you will get a voltage at A and B will be like this. Then if I look at C and D, if I see the voltage, actually we have some load here, then if you do the first cycle it will climb up like this, then it will come like this, it will come like this. This is time versus voltage, this is voltage across C and T. This is the voltage that we are getting if I start from 0 time. What is happening is, when first time when this comes positive, then the current comes here, and then at that time the capacitor voltage was not there, its capacitor was empty. So, it charges up to the peak, that this is nothing but the peak voltage of the AC. Then once it peak is charged up, then what is happening is, at the output if I see here, that is I will take this point as see with respect to C, if I take E, then at between C and E you will have the rectified voltage like this. this is between C and E. Between C and E you will have the voltage coming like this, time versus voltage. So, essentially the first cycle goes like this, it charges up to the peak, then the AC voltage drops very fast, but then the DC comes slowly because the capacitor discharges slowly, and the next cycle it charges only during this time. The next cycle again it drops like this and it charges only during this time. So, you will see that the diodes are conducting only near the peak for a small fraction of the time, this time only. That the actual conduction takes place only here. That is, it starts somewhere here and stops at the peak. Sometimes it goes little below peak also. So, you find that the diodes are conducting a fraction of every half cycle and charges of the capacitor close to the peak value. In a practical case, for example, one half cycle lasts for 10 millisecond, whether it is a 50 hertz, then one cycle is 20 millisecond, one half cycle is 10 millisecond. You will find diodes are conducting only near the peak, about 3 millisecond time. Remaining 7 millisecond diodes are not conducting. That means the diodes are actually 7 millisecond it is off. For example, with this positive half cycle the current actually goes like this, then it comes like this and then goes through this. So, even during that time only 3 millisecond they are conducting and remaining 7 millisecond it is off. Anyway, next half cycle they are totally off, the total 10 millisecond off. That means out of 20 millisecond each diode is conducting only 3 millisecond and 17 millisecond they are off. But nevertheless they charge very close to the peak value. So, the voltage that you are getting here is this secondary voltage that normally given in RMS. For example, if I have 20 volt AC, then I will get 20 into 1.414. That is roughly 28 volt DC I will get across this. This is 28 volt, then this point is 28, then depending upon the load it decreases little bit, again comes up, again goes up. So, normally we forget about the first half cycle. So, we assume that the voltage is like this, that is what we see, and that is the ripple. This is the ripple, what is the bottom, where it is discharging and stopping, and then from here next cycle start conducting and loading. So, if I see this carefully, one half cycle I will put and show you that how the diode conducts, because this is very important to select the rating for the capacitor and so on. So, if we take time and voltage, take one half cycle and then I put the next half cycle. The first cycle you leave it, then it's at this point the diodes stop the conduction, then the voltage decreases, then the decrease in capacitor voltage is taking place. At the same time the AC voltage is decreasing and reaches 0 because reached 0 and then it started rising up. Then once and this fellow started dropping, and when at some point they meet, now again diodes started conducting. So, during this time and this time diodes are not conducting. So, only during this time the diode is conducting. So, the story is that if you have 20 volt AC you will get 28 volt DC with small ripple. The ripple depends upon the load resistance. That means, if I want 28 volt, I have to specify 20 volt AC here. Now, in our discussion, if we go back to our earlier discussion, that we want 15 volt, we want 15 volt output. For that we need 18 volt here. At 18 volt is needed when the input is at 230 volt. So, to get 18 volt we need some AC voltage. The required AC voltage for 18 volt is for 18 volt DC, DC. The required AC is AC is 18 divided by 1.414. So that comes nearly 180 divided by 14. That will call for about 13 volt AC is required. That means if I have a 13 volt AC here, that will give me 18 volt DC here after rectification. But then I know that I need 18 volt when the input is 170 volt. That means I have to find out what is the voltage that I need at this point at 230 volt, because if I am giving a specification for the transformer, I should give at 230 volt what is the voltage required. So you need 13 volt AC at 170 volt, because at 170 I said to get 13, that will give me 18 here, and that will make sure I get 15 volt at the output. That is at 170 volt, at 170 volt AC input, secondary voltage is 13. So at 230 volt, input, secondary voltage actually is equal to, you will have 13 into 230 divided by 170. That is the voltage required. That if you work out, that turns out to be if I can calculate and show you. So in the next, actually you see this thing. So at 230 volt AC input, the secondary voltage is actually that 13 volt into 230 divided by 170. So if I calculate this, that actually comes, if you multiply this, you will get divided by 17, that will come, you will get 12, 19. So that will be 8 times, roughly 18 volt. So you need a secondary voltage of 18 volt is required at 230 volt. That means I had to give a transformer spec as primary 0 to 230 volt, secondary 0 to 18 volt, because at 230 you will get 18, and that will make at 170 to get 13 volt. At 170 at 170 volt here, then automatically I will get 13, and that will give me 18, and I am assured of 15 volt here. Of course, at 230 I need 18 volt, and that will give more voltage here, 18 into 1.414, does not matter, this you will still get 18. That means we have to decide on the transformer first. The transformer can be, the rating can be decided like this. So now what the voltage required is, I need to have 18 volt, that is at 230 I will get 18 volt here, and then this voltage go 18 into 1.414. So that is how the transformer has to be decided. Then the question of deciding on the capacitor here, because this capacitor also we have to decide that the value of the capacitor to be decided depending upon the load. Now how we calculate the this capacitor value? Now I can calculate the value of this capacitor by considering how much time that the energy it is, how much time it is discharging to the load, and how much time it is charging up. Now I will show you soon that in most of the cases, you can see that the conduction angle is always around 3 millisecond in 1/2 cycle. Then of course the capacitor have to discharge the remaining time, that is during 3 millisecond the diodes are supplying energy to the capacitor as well as energy to the output, and then remaining 7 millisecond the capacitor have to discharge. That means I can take the charging time of the capacitor is 3 millisecond and then discharging time as 7 millisecond. So, if the capacitor discharges for 7 millisecond, we know that the voltage will decrease, and if I put large value capacitor, then we find that the voltage decrease is small, that means ripple will be small. So, larger the value capacitor will get a smaller the ripple. But then if I keep if you keep too much large capacitor, again it is not that you are going to reduce the ripple. I will show you little later that if you keep on increasing the capacitor, you are not going to get much benefit. Of course, the ripple will come down, but the conduction angle is not going to change much, and the output voltage also will decrease. So, depending upon the ripple requirement, I have to select the capacitor. There is a small complication is there between the conduction angle and the capacitor size. Right now we will not get into that argument. However, if I put large value capacitor, you will find the smaller ripple at the point. So, the ripple voltage, so the ripple voltage is the one which decides the size of the capacitor. The ripple voltage is to be determined. So, assume that I want ripple voltage of say 3 volt. Now, if I need a ripple voltage of 3 volt, then I have to select what is the capacitor required. Now, we know that the basic formula I into T is equal to C into V. This is the basic equation governing the charge and the voltage. Now, in this case, I want ripple of the capacitor, that is how much this capacitor is discharging. So, I take C into delta V is this, then I is the load current, that is in this case 1 ampere, and the time is actually the discharge time is 7 millisecond, 7 in 10 power minus 3, because the capacitor is discharging for 7 millisecond, and while discharging 7 millisecond the voltage will decrease. That voltage is taken as delta V. So, that C actually is given by now C actually is given by 7 in 10 power minus 3 divided by delta V. So, in this case I wanted 3 volt ripple, that means 7 by 3 into 10 power minus 3, that is actually 2.3 in 10 power minus 3 farad, or that is equal to 2300 microfarad. The standard value is 2200 microfarad, that very well suits here. So, I can put 2200 microfarad, that will give me ripple voltage of 3 volt when the load current is 1 ampere. So, that is how the capacitor value is selected. Now, we have selected the transformer voltage, and then we have selected the capacitor value. Now, one thing that the diodes are conducting only for 3 millisecond, and during that time only all the energy is coming, and remaining 7 millisecond diodes are not conducting and transformer are also not giving any power, but we are getting continuously 1 ampere power at this point. That obviously puts on question that if I am drawing 1 ampere continuously, and if I am drawing power only 3 millisecond out of 10 millisecond half cycle, then obviously during that 3 millisecond more current supposed to come from the transformer, more than 1 ampere current supposed to come from the transformer. That is true, because if this is giving 1 ampere current continuously, and if this is charging only 3 millisecond, and during the 3 millisecond definitely more than 1 ampere current have to come. And this is very important, because very often we make this mistake in selecting the current rating for the transformer, because there are two additional problems that we get in this. For example, if this transformer continuously supplies 1 ampere, the heating will be less, but if it supplies say 2 ampere half the time, and other half the time if it sleeps without giving any power, you will find the heating is more. even though it had given the same amount of power during average time, during long average period of time. But if you are not taking power continuously, then heating will be more. That is what happens in this diode capacitor arrangement, because the diodes are not conducting continuously, they are drawing large power for 3 millisecond and the rest of the time it is quiet, but that makes the transformer to heat up more than the normal amount. That means, if I am designing the transformer, then if I have to rate the current rating for the transformer I have to give, that actually calls for over rating of this transformer. If I need 1 ampere here, definitely I need more than 1 ampere rating for this transformer. Now, for many students it may be a worry that finding out why the transformer have to heat up more if you are not drawing the power continuously. This is because the power loss is actually given by I squared R is the power loss, whereas where I is the current and R is the resistance, the equivalent resistance of the transformer. Take in this case only the secondary resistance alone. Assume that I have resistance as 1 ohm, R is equal to 1 ohm, and then I need load current I need 1 ampere. Now assume I am taking only 3 millisecond current, then the peak current is much more than 1 ampere. Let us assume during 3 millisecond I am drawing average current of 3 ampere. That means in this case the same I can take heat loss in 2 cases, that is assuming I am taking continuously 1 ampere current from here. If I am taking 1 ampere current from the transformer continuously, then what is the power loss I calculate. Then next case I assume the transformer is conducting only 1/3 of a time, but it is taking 3 ampere current. So 1 ampere current, it delivers 3 ampere current for 1/3 of a time. That means total power that drawn is same in both cases. So we take 2 cases and find out in which case the heating is more. So what I do is I will take these 2 examples. See, case 1. Case 1, continuously power is taken, that is continuous power, continuous 1 ampere continuously taking, and case 2 3 ampere for 1/3 of time. 1/3 of a time I am taking 3 ampere, that means average power is same in both cases. Now here I squared R, if I find I squared R in this case will be 1 square and R is 1 ohm, that I will have 1 watt power dissipation. Now in this case that I will have I square, that is 3 ampere, that is 9, that is if I take I square, that is 3 squared into R, that is then of course we have only 1/3 of a time it is conducting, so I have to divide this by 3. So here in this case 9 into R is 1, so we get 3, that is equal to 3 watt. That means in this case we had a heat dissipation of 1 watt, and if I take 3 ampere for 1/3 of a time, then heat dissipation is 3 watt. So it is better to take the power continuously rather than in the pulsed form. When you are taking current in the pulsed form, more heating is taking place. But then if you go back and see, we have no choice, because if once you put the regulator, once you put the once you put the diode and capacitor, the current comes only in the pulsed form. That means you will have more heating on the transformer, that automatically happens. Now, only choice that we have is that we design a transformer such that it takes it accepts that much heat. The other way around of telling this would be, I overrate the transformer. That is, if I want 1 ampere current, then I put more than 1 ampere rating for this transformer. I can show you in some other calculations later that for the transformer of bridge rectifier, I need to rate 1.8 times actually. That is, if I want 1 ampere current, if for 1 ampere load, secondary current requirement will be 1 ampere into 1.8 times. Now, you ask what is this 1.8? That is, for example, in this case I will put 1.8 ampere rating. That is, instead of 1 ampere I will give 1.8 rating. That means you are going to use a thicker wire and the heating going to come down. Of course, how many times you have to overrate depends upon what is the conduction angle. If the conduction angle is smaller, then overrating has to be more. The conduction angle is more, then the overrating need not be more, because if the conduction angle is more means is more or less it is conducting continuously. So, depending upon the conduction angle, I have to overrate the transformer. Now, you will be surprised later that even if I change this 2200 mF to 4700 mF, you will find the conduction angle almost remains same, because in our classical textbooks there is one misconception that if you increase the capacitor value, the conduction angle will come down. That is not really true. That is true only for ideal transformer. For a practical transformer, by increasing this you cannot actually reduce the conduction angle. This happens because, for example, if I put 1 farad capacitor here, then the ripple is almost 0. That means conduction angle will be very narrow, that you may get few microsecond only conduction angle. For example, if I put 1 farad capacitor, the conduction angle comes to few microsecond. Obviously, the transformer will not be able to charge this capacitor of 1 farad in few microsecond. So, you will find the conduction angle still remains close to 3 millisecond only, and this needs a big explanation, and right at this point of time we will not look at it. You will find for practical values of 2200 microfarad or 4100 microfarad or 10,000 microfarad, you will find the conduction angle is almost close to 3 millisecond only. So, the classical misconception that if you increase the capacitor value, that conduction angle will come down and the current will shoot up, that is not correct. You can practically see, increase this capacitor and you will find the conduction angle remains 3 millisecond more or less, and the current also only about 3 times the load current. So, considering this, this factor of 1.8 was selected, and we can show using a recursive mathematics how this 1.8 ampere had come, and that is not required at this point of time. We will see that at later time. So, all that we would say is for most of the practical cases we need to have overrating of 1.8 times. So, that decides what is the rating required for the transformer. That is, in this case for 1 ampere and 15 volt output, I need 18 volt and 1.8 ampere current rating for this transformer, and I need a 2200 microfarad capacitor to work with this. So, that decides what is the capacitor size and the transformer and so on. Now, we have to go and decide on various other components, particularly the heat sink, and then what type of transistor I have to use, why I need Arlington pair, and then if I use different op amps, 741 or 714, like that, if I use different operational amplifier, what happens, that remains to be seen. Similarly, I have to worry why I need this capacitor. Now it looks that designing a simple regulator seems to be very complicated, but actually it is not that way. We will show you that some more complications, that in case if I ground the output accidentally, for example if you have a load here and if I accidentally ground this, then I know that this goes to 0 and then this goes to 0, then this is sitting anyway at 5, and that make the output voltage go very high, because the difference is now 5 volt. The 5 into open loop gain will be high, and this will go to 20 volt, and that will come to 20, and then that will come to 19.4, and this is 0 and the 19.4. Then first this transistor goes bad, then once that goes bad, this also goes bad. So invariably if we short this and the transistors go bad. That means we also had to provide a short circuit protection. Particularly it happens the short automatically at the beginning. At the beginning this capacitor is empty, this is not charged. So large current runs through that, it acts like a short, and most of the cases as soon as switch on, this regulator goes bad. Even though as a textbook circuit it is okay, but then practically if I do not provide a short circuit protection, it goes bad. You will never able to use this regulator. So we also have to provide a short circuit protection. So also we have to decide on this resistor and then this resistor, and then also I may ask, why did you select 10k here 20k and 10k? I can also have 1k and 2k, like that. There are so many questions come in, and all these things have to be answered. So one need not get frightened with with a simple regulator like this. So many design issues are there. It is natural that design involves putting very many comments, and that comments must be perfect in all respect, and that is actually the design. So learning electronic circuit without getting into design is very simple, but that is useless. So your focus would be always how to design a circuit, how to select the different values, and then what is the extreme conditions, when it will fail, and so what happens when the mains voltage changes, and then what is really happening, and that should be looked into that very carefully. Then only the design will be complete. In fact, the focus of this the entire course will be like this only, that everything we will be getting into details, and then we will select the values considering very many factors. Now for example in this case we had selected the transformer and then the specification related to that. Now let us see how how will you select, how will you design this transformer itself. That is another question, because many times you may say I may give a specification for the transformer manufacturer and give this one. But then that is only half the story, because if you are a power supply manufacturer, you will find cost of this transistor, then cost of this operational amplifier, and all this electronic component. If we take, the cost is very small. Most of the cost goes only to the transformer. And if you are buying a transformer from you order the transformer and getting it from your supplier, you will find that all the money actually goes to the transformer manufacturer, and as a voltage regulator manufacturer you will get nothing at all. So if you are in a practical world, if you are making a regulator, a voltage regulator, then you must also make the transformer. And as an analog circuit designer, you should know how to design the transformer also. If you don't know how to design a transformer, then really there is no use in studying the voltage regulator, because you are studying the voltage regulator only with the intention to produce them. Because all our circuits that what we are going to discuss, that I will assume that you are running an industry, and for the industry you are developing that product. That is the approach that I am going to take throughout this course. I am not going to teach you from the academic point of view how the circuit works and write the equation and then move on from there. and as far as I am concerned that is useless, and I advise you not to do not to take that kind of approach. That will ruin you in over a period of time. That is what happens. That is what happens in happens as in many times. When we study in our college, that is what we have done. We have actually taken approach that we want to understand the circuit. That is not a correct approach. We have to assume that I am going to manufacture this circuit, and for that how I am going to what are the things I have to learn, and how I have to optimize the cost and so on. So that is what we are going to do. So next we will take up how to decide the value of R1 and this resistor. Then how to select the value of this, and then which transistor you will select, and how will you select the heat sink for this. Then also I will discuss how will you design this transformer itself, because that transformer design learning will help you at many places, because in analog circuit we will be designing transformer for very many purpose. Like for example, when I want to make a oscillator, I will have to design a transformer, and then we also have to design a filter. That time I need to design an inductor. For the inductor design I had to know I had to anyway learn how to wind a coil and so on. So that way learning how to design a transformer also will be of very great help to you in future. So the next class I will talk about how to design various other components that is associated with this, and then also tell you how to design the transformer in a simpler way. To design a transformer you do not need any computer or any calculator. You can, I will show you how to design it very easily. Then you can look back and see how the textbooks are shown how to design the transformer. So with this I will stop this lecture. We will continue in the next class. Thank you.